Hello everyone, it's my great pleasure to be here today to present our recent work, all-in-one, visual description guided unified point cloud segmentation. As we know, point clouds are now widely used in many fields because of their high precision and geometry stability. They are less affected by lighting or appearance and provide accurate 3D measurements with dense spatial sampling. Typical applications include autonomous driving, robotics, and remote sensing. The core step in this field is point cloud segmentation, which aims to organize raw, unordered 3D points into meaningful semantic structures. We can roughly divide it into three tasks: semantic, instance, and panoptic segmentation. Most existing point cloud segmentation methods can handle only one task at a time. However, in real-world applications, we often need a unified model that can perform multiple segmentation tasks together. Inspired by OneFormer in the image domain, OneFormer 3D was proposed to unify semantic, instance, and panoptic segmentation within a single framework. It adopts a transformer-based architecture, using semantic queries and instance queries to generate their respective masks, and the panoptic results are simply obtained by merging them. Although these previous methods have made great progress, they still face several common challenges. First, point clouds are inherently sparse and lack semantic and contextual information. High-quality 3D annotations are also limited, which greatly constrains model training. Second, even unified models like OneFormer 3D still struggle with fine-grained semantic understanding, making it hard to capture rich scene semantics. Moreover, existing multimodal 3D methods often rely on paired multi-view images and online to D3D alignment, which are costly and complex to implement. To address these issues, we propose a new idea. We leverage large language models to generate rich semantic descriptions that complement the limited semantics of point clouds. At the same time, we use internet images to introduce fine-grained visual details, compensating for the sparse and textureless nature of 3D data. By combining these two sources of external knowledge, we can significantly improve 3D segmentation without heavy annotations. This is the overall framework of our method. Next, let's take a closer look at each component in detail. First, let me introduce the Spatial Enhancement module. The goal of this module is to capture spatial relationships among points in the point cloud. Since raw point clouds are sparse and unordered, focusing only on local regions may cause the model to lose the global spatial structure. To address this, we adopt a sparse attention mechanism. Each point feature is projected into query, key, and value vectors. Instead of computing attention over all points globally, we randomly sample a subset and calculate attention only within it. This design not only preserves the overall spatial structure, but also significantly reduces computation. Finally, the enhanced spatial features are obtained through weighted aggregation. Then, following the idea of OneFormer 3D, we sample instance queries from the super points. Next, to further enrich the semantic information, we introduce LLM-generated descriptive queries. Specifically, we design a language-driven description generator, called LLM Deskin, which produces fine-grained visual semantic descriptions for each category. For example, instead of just labeling something as chair, the LLM provides a more detailed description, including its appearance, material, or usage context. This helps the model better distinguish between visually similar classes. After obtaining these descriptions, we use a text encoder, such as CLIP, to convert them into embedding vectors as semantic queries. These queries then interact with the point cloud features, enabling the model to generate more accurate and fine-grained masks during semantic segmentation. At the same time, we also use internet images as queries. Unlike previous methods that rely on paired multi-view images, our approach directly collects a set of reference images for each category from the web. We then extract their features using the image encoder of CLIP, which greatly reduces the need for costly annotations. In our model, we combine two types of queries. The descriptive queries provide high-level semantic understanding, while the image queries supply fine-grained visual details. Together, they complement each other and enable the model to learn more discriminative and robust representations. After constructing the instance queries, descriptive queries, and image reference queries, we feed them into a feature fusion module to enable cross-modal interaction and integration. Through this module, information from different modalities is effectively aligned and fused. The model then uses these fused queries to generate the corresponding prediction masks, thereby achieving multimodal condition segmentation. Finally, to obtain a more robust semantic segmentation result, we design a multimodal ensemble strategy. For each point, the model first generates semantic prediction scores from both the descriptive queries and the image queries. We then apply max pooling to select the most consistent semantic prediction and fuse the two results to produce the final semantic label for that point. In this way, the descriptive queries provide high-level semantic discrimination, while the image queries add fine-grained visual details. By combining their strengths, the model achieves both better class accuracy and richer segmentation details. To achieve effective multimodal feature fusion, we design a semantic visual contrastive loss. For each point feature, we encourage it to stay close to the text and image embeddings of the same category, while keeping it far away from embeddings of different categories. This design enhances the semantic consistency of point features, helping the model better understand the meaning of each class, while also improving class separability and reducing confusion between similar categories. Moreover, it fuses both language and visual information into the 3D features, leading to more robust and discriminative segmentation results. This slide shows the overall framework of our method, which consists of 3 main steps. First, we extract point features and enhance global perception through the Spatial Enhancement module. Second, we construct 3 types of queries: the instance queries, the LLM-generated descriptive queries, and the image queries collected from Internet reference images. Third, we feed these queries and point features into a unified multimodal decoder, where information is fused and predictions are generated. Finally, we apply an ensemble strategy to combine results from the descriptive and image queries, achieving both accurate semantic discrimination and fine-grained detail. With this design, our method can perform semantic, instance, and panoptic segmentation simultaneously. We conduct experiments on 3 benchmark datasets: S3DIS, ScanIt, and ScanNet200. For evaluation, we use task-specific metrics: mean average precision for instance segmentation, mean intersection over union for semantic segmentation, and panoptic quality for panoptic segmentation. First, we show the results on the S3DIS dataset, which contains 6 indoor areas. The upper table shows the results under the Area 5 validation setting, where we train on 5 areas and test on the remaining 1. The lower table shows the results under 6-fold cross-validation, where each area is used once as the test set in rotation. As we can see, our method achieves the best performance across all 3 tasks: instance segmentation, semantic segmentation, and panoptic segmentation, demonstrating strong generalization and unified capability. Next, we present the results on the ScanIt dataset. The upper table shows the results on the validation split, while the lower table reports the scores on the hidden test split, which are obtained by submitting our predictions to the online evaluation server. As shown, our method achieves the overall better performance across all metrics. Finally, on the ScanNet200 dataset, which includes more fine-grained categories, our method achieves the best performance across all tasks, showing its strong generalization to complex, large-scale scenes. Next, we show the ablation study. As we can see, each component, including spatial enhancement, description query, image query, and CVC loss, contributes to the final performance. Removing any of them leads to a clear drop, which shows that these modules complement each other and together make our framework more effective. Next, we show the qualitative results. Compared with OneFormer 3D, our method produces more accurate and consistent segmentation. Thank you for your attention. That's all for my presentation.